So in this video, I'm going to be showing you how to calculate an expression that represents the pressure on the end cap of a sideways cylinder. This is useful for things like barrels or tanks, where you need to know how much pressure the tank needs to resist in order to build it so it doesn't explode. So before I dive into calculating the pressure on the cap, I'm actually going to calculate the pressure on this outside curved part to kind of help us conceptualize what we're going to do when we move to the cap, because it's a little easier. So if we were to just calculate the pressure of this outside curved surface, then we'd have to kind of add up all the pressures and they'd be going in different directions along like the outside of that curved surface. So to kind of simplify this, I'm going to redraw the cylinder and kind of divide it in half here using a rectangle. So there's a cylinder and then the rectangle is kind of stuck in the middle of it here. And so what this rectangle looks like is it matches the length of the cylinder and it's 2r tall. So then we also have the height of our fluid in here, which is still h. And then from here, we need to add up all the pressures. So kind of what this looks like in equation form is to get the force against the surface, we're going to add up all the pressures that's kind of going along the surface. So as we kind of move horizontal across the cylinder, the pressures aren't going to change, but when we move up and down, that's when it changes, because we have height in our pressure equation here. So how we're going to go about this is I'm going to divide this rectangle up into a bunch of tiny slivers with a height of dh, and add up the pressures that are against those areas. So what this is going to look like is the force on the curved surface is going to be the integral. I'm going to substitute these values in for pressure. So it's going to be rho g h. And then to get the change in area, or the differential area, it's going to be the length times this small, a little bit of height, dh. So L dh. And then from here, we can just kind of pull out all the constants, which are rho, g, and the length of the cylinder. And then left in our integral is just h dh. So from here, we could just integrate that expression, and we'll get the expression for the force on the curve. So still our constants out front, integrate h with respect to dh, it's just going to be 1/2 h squared. And then this is only for one side of the cylinder, since we're just calculating it against this flat surface. To get the other side, we just have to double it, multiply by 2. So the force on the curve is going to be equal to rho g L h squared. Right? And so now, kind of keeping this concept in mind, how we split up the rectangle into little slivers of height, we're going to do a similar thing with the end cap. So once I find my eraser, I'm going to erase all this to give myself some space to work. And then just rewrite the equation for the force, which is just summing up all the pressures against the area. Now from here, taking a look at the end cap, we have the center point and radius r. We also have the height of the liquid, which is h. And we need to kind of get this equation in terms of values we can work with. So I'm going to use polar coordinates. Since it's a circle, it'll make the math a little bit easier. So basically we want everything in terms of r. So I guess I'll just start with h. To get h in terms of r, we're going to kind of divide the circle up this way. And you can kind of think of this area as the rectangle that we use to calculate the pressure on the curved surface. So to get the equation for the height, it's just going to be the radius plus this little sliver here. And thinking back to the unit circle, this is just r cosine theta. So for our height, just going to be r, which is this section, plus r cosine theta. Oh, this is r sine of theta. Which gives us this vertical component. So when you add these two together, that gives you the height of the liquid. And then go ahead and divide this area up into little slivers of dH. And then from here, we can differentiate this equation to get the expression for dH. So derivative of r, which is a constant, is just 0, plus a constant times the derivative of sine is cosine. So dH just equals r cosine of theta. And now from here, to get the area, we need to multiply it by the width of this section. Similarly to how we multiply the length of the cylinder times dH for the curved section. And the expression for the width, it's just this distance here. And that is just r times the cosine of theta. So it's just the horizontal component. Now from here, we can go ahead and substitute all of our values into this equation. So the force on the cap is going to be equal to rho g h, which is this equation here, r plus r sine of theta, times the area of this little sliver, which is just the width times dH. So r cosine times r cosine is just r squared cosine squared. And we're in polar coordinates, so we're differentiating with respect to theta. Now from here, I'm just going to pull out some of the constants and clean this equation up. So we can pull out rho and g. And then if you notice, there's an r term in this expression and an r term over here. So if we pull all those out, it is r cubed. Since the radius is constant, we can pull it out. And then this is just 1 plus sine of theta, and basically just get rid of that. And so to kind of simplify it a little bit further, in the integral, we're going to have 1 times cosine squared theta, which is just cosine squared theta, plus sine times cosine squared theta. So this is the integral that we're going to be solving to get the equation for the force on the cap. But first, before we integrate, we need to define our bounds of integration. So it'll be from this point here down to this point here. So I'll split that up into different theta values. So this theta value, theta 1, to this theta value, which is theta 2. And now for the actual values of these, theta 2 is easy. It's just from 0 degrees down to negative 90. So it's just negative pi over 2. And then for theta 1, it's going to be a little different. We can come back to our trig identities using the adjacent side over the hypotenuse. The hypotenuse is just r. So since we're using sine, it's going to be arc sine. R is the denominator, and then this distance up here is just going to be h minus r. All right, if you take away r from h, which is this whole distance, it just gives you this sliver here. And so that is the expression for theta 1. And now we can integrate. So these integrals are a little messy. You need to do some trig substitution in order to solve them. But I just went ahead and plugged them into the equation solver like Wolfram Alpha to get the different equations. Hold on, my cat is chewing on my table. Stop it. Say hi to Yoshi. Now from here, again, taking the integrals, we still have our constants out front. The integral of cosine squared theta is just 1/2 theta plus 1/2 sine theta cosine theta. And then the derivative of sine times cosine squared theta is just -1/3 cosine cubed theta. And we're evaluating it from theta1 to theta2. So it looks like this. Now I'm gonna erase some of this so we have room to evaluate this integral. And so from here, we have the force on the cap is going to be equal to our constants, rho g r cubed, times, if we plug theta2 in, which is just -pi/2, that's easy because all the terms with cosine just go to 0, because cosine of -pi/2 is 0, and we're just left with this one term. So 1/2 times -pi/2 is just -pi/4. But plugging in theta1 isn't going to be as easy. So I'm going to kind of define them separately, define cosine of theta1 and sine of theta1. So sine of theta1, if we plug this into sine, the sine and arc sine cancels out. We're just left with h minus r over r. Now for cosine of theta1, we can't just plug it in because then we'd have the cosine of the arc sine of this, and that's a little bit more difficult to kind of figure out. And so to express this, I'm going to actually use a trig identity. So cosine squared theta plus sine squared theta equals 1. And since we know what sine of theta1 is, we can use that to find cosine of theta1. So cosine squared theta is going to be equal to 1 minus sine squared theta. And so we have 1 minus sine squared, which is h minus r squared over r squared. And then to get rid of the cosine squared, we just take the square root. So this is cosine 1. So I'm going to kind of get a common denominator. I've got the squared here. Get a common denominator and multiply this top out, and some of the terms are going to cancel out nicely. So getting the common denominator, we have r squared here over r squared, and then I'm just going to multiply this out. So minus h squared, double the second, so we have 2hr, and then square the last. This is all under square root. So these terms are going to cancel out. R squared minus r squared is just 0. And we're left with this. So cosine is going to be the square root of 2hr minus h squared over square root of r squared is just r. So again, I'm going to kind of erase this, clean it up. Now we can kind of plug this back in and plug theta1 into our equation. So theta1 times 1/2, we're just going to have minus 1/2. Theta1 is the arc sine of h minus r over r. 1/2 sine theta times cosine theta is just going to be plus 1/2 sine of theta1 is h minus r over r. Cosine of theta1 is the square root of 2hr minus h squared over r, and then minus 1/3 cosine cubed. So 1/3 cosine cubed theta is just this expression cubed. So we're going to have 2hr minus h squared all raised to the 3 over 2 over r cubed. So this is the expression for the force on the cap. So I'm just going to kind of rewrite it so it's a little easier to see. Hopefully I have enough room, kind of in the middle here. I think I need a bigger whiteboard for this problem. 2h minus h squared over r minus, let's do it down here, minus 1 over 3 2h minus h squared 3 over 2 over r cubed. So this equation right here This equation here is the equation for the force on the end.